Hello, grade 11. So this week we are starting with the second part of the chapter that has to do with the projectile motion. Let's start. So yeah, we're going to apply Newton's second law to determine the equations of motion of a projectile. So what is a projectile motion? You can see we have three cases. The first two cases we already mentioned. The first one is the case of a free fall body, okay, where the initial velocity is a vertical downwards. This is v0. And the second case where you simply, give it an initial velocity vertical upwards. This is the second case. And the third case, which is the case that we're going to study today, it is the general case, okay, where the initial velocity given is making an angle alpha with the horizontal, and you can see it this way. So yeah, and now let's click on the simulation to view a projectile motion. Okay, so it's gonna open up to this page. Go to intro. All right, so you can see a cannon and you can set the height as much as you want. I'm gonna put it at 0 and you can, just play with the angle. Okay, so I'm gonna set it to any angle. We haven't started with the calculations yet. So we are here just to view how projectile works. Okay, so you can see I can change the angle and I can in the simulation choose the object that I'm going to fire. So I'm going to choose a human. All right, I'm going to put it in slow motion and yeah, so let's fire that. So you guys can see this is a projectile. So yeah, it's moving only under the action of its weight. We are giving it an initial velocity and this is the trajectory that it takes. So yeah, let's start the calculations. So basically this lecture contains a general exercise that includes all what we might be asked to find when we're dealing with a projectile motion. Okay? So let us consider an object that is moving by the effect of its own weight only. Okay, and it has an initial velocity in any direction, and you can see that it makes an angle alpha with the horizontal. This is the initial velocity. Okay, and this is what we call a projectile, basically. So a ball is thrown at an instant taken as origin of time at t0 equals to 0. From a point O taken as origin, you can see the point where we first launched the ball was taken as the origin, okay, and then you have the reference frame, the x and the y axis, and yeah, you have an initial velocity that makes an angle alpha with the horizontal. Let's start with the initial conditions, the position. Let's talk about the x0 and the y0. You guys can see it started from the origin, so its x0 and y0 are both, zeros. Okay, how about the velocity, the initial velocity, v0? Like in the previous exercises, we used to say, okay, so v0 equals 10 meters per second, and that's it. But in this case, you guys can see that v0, it has two components, an x component and a y component. Okay, so you guys can project it on the x-axis and you'll get a component, and you can project it on the y-axis and you'll get another component. So you can see it has a v0x and a v0y. So the v0x, it is adjacent to this alpha, so it will be v0 cosine alpha, and the v0y is opposite, okay, because it is the same as this side, and it will be v0 sine alpha. So the velocity in this case, the initial velocity, it has two components, v0x, v0y. As a vector, I can write it v0xi, this is the x component, v0yj, this is the y component. okay, where v0x equals v0 cosine alpha, v0y equals v0 sine alpha. Now it's time for me to find the acceleration. So to find the acceleration, I have to list the forces acting on this body, right? So the forces, we only have the weight. We don't have any other force, so I can write that I will apply Newton's second law, which is the summation of all the external forces equals ma. So mg equals ma. Perfect. But in this case, since we're dealing with a planar motion, and you guys can see we're dealing with a planar motion, and the ball is not moving on a straight line, so the acceleration that we have right here is not the same as usual. Guys, usually when we were working with a straight line, with a rectilinear motion, the acceleration was, in the direction of, parallel to the direction of motion. So when we project along the direction of motion, we always get ma, and that is it. But in this case, the acceleration also has two components. So the acceleration, it has an x component and a y component. So I can write it a equals axi plus ayj, because now we're dealing with a planar motion. And the weight, it has only one component, which is in the y direction. Okay, so it has only a j component, a y component. This is why we write it minus mgj, because you can see it is opposite to the positive direction of the y-axis. And yeah, basically that's it. We can substitute now, and you can see we have I and J. We can't be doing anything anymore. All we can do right now is to compare. So we can see I have MAXI, but I don't have any I component on the other side. So MAX equals to 0, and this gives me that AX equals to 0. Whereas for the y, MAY equals minus MG, because these are the J components. So I have that. And then AY will be equal to minus G, because the M, they cancel each other. So now moving on to the nature of motion, like usual, after finding the acceleration, I need to see whether it is equal to 0, different from 0, and such. So let's start with the parametric equations, or the nature of motion along the x-axis first. Along the x-axis, we found that the acceleration ax equals to 0. The initial velocity was not equal to 0. Okay, and this gives us that the motion is uniform rectilinear motion. Okay, so in a uniform rectilinear motion, what is the equation of motion that we have? You guys remember, it's x equals v t plus x0. Now, we didn't write back then vx, but now we're going to do that, okay? Because when we're dealing with the x-axis, we're going to write vx, ax, and when dealing with the y-axis, we're going to write vy, ay, and such. All right, so we have this equation. How about the velocity? I'm dealing with the parametric equations of motion. I want to find the velocity as a function of time, and I want to find the position as a function of time. So as for the velocity in the uniform rectilinear motion, it is constant. And I already have v0x, which is the initial velocity. So the velocity is constant, so vx that you have right here is constant, and it is equal to v0x because we already have it, which was v0 cosine alpha. Now I can substitute vx in here, and x0, it is equal to 0. We already know it because the initial position was 0, 0. So yeah, we can substitute. So x equals v0 cosine alpha t. Now along the y-axis, we can see that the acceleration equals to minus a g. So ay equals minus g, which is not equal to 0. So the motion is uniformly varied rectilinear motion. And yeah, so if I want to find the parametric equations of motion, I want to find them relative to the position and relative to the velocity. So starting with the velocity, we know it. Vy equals ayt plus v0y. Everything relative to the y-axis. Let's see what I do have. So ay, I already have it. V0y, you guys, we already found it. Okay, so we have everything. We just substitute. And there you go, Vy equals minus gt plus V0 sine alpha. We substituted, that's it. Now the other equation, which is relative to the position. Okay, so there you go. We already know it. We know ay, we know v0y, and y0 it is equal to 0 because this is the the initial position. So we substitute everything, and this is, guys, what we get. Y equals minus half gt squared plus v0 sine alpha t. Okay, so we're only substituting this. We're doing the same work we used to do in the case of a rectilinear motion. Okay, but the only difference now is that I'm doing it along the x-axis alone and then along the y-axis alone. Okay, so now trajectory. We didn't do that in the case of a rectilinear motion because we know that a trajectory is a straight line. There is no need for me to find the equation for it. But now, since we're dealing with a planar motion, the trajectory is not a straight line, and we are interested in finding the equation for this trajectory. Okay, so, but the whole trajectory thing is not a new thing. Okay, so we already know that for us to find the trajectory, we have to find a relation between x and y independent of time, if you guys remember from the previous chapter. So we had the x and the y, which were the parametric equations of motion, and we have them here. We just found the x and we just found the y. So we have them both, and all we need to do is to find a relation between them that doesn't include time. Okay, so I want to get rid of the t that I have. So it's better that we start with the x, and because it contains t and not t squared. So we take the x component that is equal v0 cosine alpha t, and we want to find t function of x. So t equals x over v0 cosine alpha, and now we can substitute in y. So we can take this t, and instead of having t in y, I'm gonna have this component, x over v0 cosine alpha. So this is what I did. I just substituted, okay? And yeah, so you square this, you square this, you square this, and here v0 and v0, they cancel each other, and you have sine over cosine. Okay, so this is equal to tangent alpha x. So yeah, this is what you get. All right, and yeah, so basically this is the equation of a what? Is it the equation of a straight line, or is it in the form of ax squared plus bx plus c? Yes, so this is the equation of a parabola. So the trajectory has the shape of a parabola, and you guys can see it. It is obvious, okay? Now, one of the properties that we are interested in a projectile is its maximum height, which is basically the maximum, like I will be dealing with the maximum point that is reached by this projectile. Now, we've talked about the maximum height in a free fall exercise before, and I've said that the velocity at the maximum point is 0. Now, we didn't specify whether it was Vx or Vy because we had only one component for the velocity in that exercise, and it was Vy. So in this case, since the velocity, it has two components, we're dealing with planar motion. So the at maximum height, the Vy will be 0, okay, whereas the Vx will be different from 0. Okay, so I have an x component, you can see, parallel to the x-axis, so this is an x component, but the Vy is the one that is equal to 0. Okay, so yeah. Now that I have this, all I'm trying to find is the maximum height of the projectile. Okay, so maximum height, it means I'm trying to find the y, the position of the projectile at this point. You know, the position, it depends where I'm at, okay, so I'm trying to find it at this point, which is basically the maximum height. So Vy equals to 0, but what is Vy? We already found it. Vy is equal to minus gt plus v0 sine alpha. We already have it. We're going to put it equal to 0. And from this equation, I can find the time. Okay, so I can find that the time equals to v0 sine alpha over g. So now I have the time. I can substitute it where? I need to find y. Okay, and I have it as a function of time. You guys know it? All right, so this is the y as a function of time. All I need to do now is substitute this t in here and you'll get the maximum height. Okay, so yeah, I substituted and yeah, so we square them. V squared, okay, and here it becomes also v0 squared sine squared. Okay, so there you go. You'll have something like this. And you guys can see. So this is like minus half v0 squared sine alpha squared over g plus v0 squared sine alpha squared over g. So they are the same. Okay, so minus half plus 1, it is plus half v squared sine squared alpha over g. Okay, so this is the maximum height that the projectile, can get to. This is how we find it. Now you guys go and click on this simulation in the PowerPoint PDF that I uploaded, and let's go to the next slide. Okay, so it's gonna open up to this page. Go to vectors, choose that. All right, so first of all, I'm gonna set the initial speed to 15. You can see this cannon, okay? And yeah, I'll be choosing a random angle, let's say 40. And I will be looking at the velocity vector components, okay? I will set it to slow motion so that we can track, you guys can see once it reaches its maximum height, we're going to see that. See? So once it reaches its maximum height, I have no longer Vy. Okay, you can see only the x component. The Vy simply disappears, and then of course it reappears once it continues its motion. Okay, let's try that at a different angle. Okay, maybe a higher initial speed. Okay, so yeah, we have Vx and Vy, two components, and then when it reaches its maximum height, you have no Vy, no more Vy, and this is how we find the maximum height that it can reach. So the other property that we are interested in a projectile is the range of a projectile. So the range is the distance between the launch point O and the point where the projectile meets the horizontal passing through O again, which is the x-axis. Okay, so it is the distance between O and where the projectile meets the x-axis again. In this case, I called it A. So this is the distance that I'm talking about, and it is called range. It is the distance OA, and it is equal to the position of A. Now, it is actually equal to xa minus xo, but in this case, we can see that xo is equal to 0, and this is why the range is equal directly to xa. Now, guys, talking about ya, what is the ordinate of this point? It is 0. It is found on the x-axis, so its y is 0. Great, so we have this given we can start with. Now to find the range, there are actually two ways we can find the range. I'm going to do it using the equation of the trajectory that we just found, but you guys can do it using the same method that I used to find the maximum height. Okay, using the y to find a specific time and then substituting this time in the x equation that I have. but I'll be doing it in another way here. So I'm gonna bring out the trajectory equation that we found. This equation is the equation of the parabola that you guys can see right here. And I have this point A that belongs to this parabola. It belongs to this trajectory. So if I substituted XA and YA in this equation, it will satisfy it, okay? So yeah, and this is what I will do. But before doing that, I took X common because I have X squared and X, I took X common, and yeah, I put the rest inside the brackets. So at point A, I can substitute XA and YA into this equation. And we know that YA equals to 0, so the whole equation will be equal to 0. So you have XA into this equals to 0. This gives us that XA equal to 0, okay, but it's not actually XA that is equal to 0. X equals to 0, this is the launching point. We know that this trajectory, it meets the x-axis in 2 points. So the x equals to 0, they found the first point, which I'm not interested in. I'm trying to find the second one, which is XA. So I'm going to write this one equals to 0. Great. Now I want to find XA. So XA would be equal to, if you took this component to the other side, okay, and then you found XA, you would get tangent alpha to V0 squared cosine squared alpha over G. And then you have the tangent alpha is equal to sine alpha over cosine alpha. Okay, so you have it right here. So cosine and one of those cosines will cancel each other, and you'll have something like this. You guys remember to cosine alpha, sine alpha is equal to what? There is a relation for it. So it is in math, in trigonometry. So it is sine to alpha equals 2 cosine alpha sine alpha. So instead of that, I can substitute it with this one. And there you go. This is the equation of the range that I have. So R equals, which is XA, and it is equal to V0 squared sine 2 alpha over G. This is the range. So before continuing to some special cases in the range that we just talked about, I will be explaining or reviewing that trigonometric circle with you so that I can make sure you guys understand how we deal with sine and cosine. So it is a circle of radius 1. You can see that the x-axis is the cosine axis and the y-axis is the sine axis. And you can see that the maximum value that a sine can get is 1 and the maximum value that a cosine can get is 1. So let's say I have a point on this trigonometric circle and this point makes an angle alpha with the cosine axis, okay? It will have two components, the x components and the y component. Let's call them its coordinates, okay? So the x component is going to be cosine this angle, cosine alpha, and the y component is going to be sine alpha, okay? And you guys can see it on a drawing also, okay? So this is the y component sine alpha. Let's say I have another angle and this angle makes, I have another point and this point makes an angle pi minus alpha. So pi is 180 degrees minus alpha. This small thing is alpha. So you'll get this one. Okay, so pi minus alpha. Same thing. So this will have two components, the x and the y. The x will be cosine pi minus alpha and the y will be sine pi minus alpha. Okay, just like that. But you guys notice that the y for point M and for point M, they are the same. Okay, they are at the same point. So we conclude that sine alpha is the same as sine pi minus alpha. Okay, and this is the thing, this is the property that we are going to use in the upcoming slides. Okay, how about when will I get the maximum value of the sine? Like at which angle? You guys can see when the angle is right here, right? When M is at this point and the angle is right here, like this is alpha now. Okay, so what is this angle? It is 90 degrees. Okay, and in radians, it is pi over 2. So at this angle, pi over 2 or 90 degrees, I'll get the maximum value for the sine, which is 1. Now we already found the range, which was equal to v0 squared sine 2 alpha over g. We will be talking about the maximum range. Guys, when you're launching a ball, okay, you want to know how far this ball can get. Like, what is the perfect condition for this ball to get as far as possible. Okay, although the launching speed that you're giving it, the launching velocity, it's the same. It is constant. You don't change that. Okay, so the speed, the velocity v0 is constant, and the g is constant. So the only thing that I can actually change is the launching angle. Okay, so the angle that is between the velocity vector and the x-axis. And yeah, so for me to get a maximum range, I need the sine to alpha to be maximum. So what is the maximum value of sine to alpha? It is 1. All right, so the maximum value is 1. And when do I get this one? When this angle is how much? We've already seen it when this angle equal to 90 degrees or pi over 2. Okay, so alpha equals to 90 over 2, which is 45 degrees. And you can see it on the purple line. When the angle was 45 degrees, the range was at its maximum. So this is the maximum range, okay? And all these numbers that you guys can see are in the case of a velocity equals to 20 meters per second. Okay, so this is like a specific example. This drawing that you see here is a specific example. Okay, so yeah. So if you guys substitute sine 2 alpha equals to 1 into this one, you'll get that the maximum range is v0 squared over g, and this is the case for alpha equals 45 degrees, okay? All right, so now that we know if we want to find the maximum range, we have to have a launching angle of 45 degrees. Okay, let's see what happens with the range for complementary angles. What are complementary angles? Let's say I have two angles, alpha and beta. So alpha plus beta equals to 90 degrees or pi over 2 in radians. So alpha and beta are complementary angles because when we add them together, we get a 90 degrees. Okay, so let's say I have an angle alpha of, so I have an angle alpha. If I want to find the range for it, it would be this expression, which we already found. Now let's try to find the range for beta. So beta is equal to pi over 2 minus alpha. So for an angle pi over 2 minus alpha, which is the complementary angle of alpha, I can substitute instead of alpha that I have right here. Okay, I'm gonna write pi over 2 minus alpha. So instead of that, I wrote pi over 2 minus alpha. You can see that. And then you multiply by 2, so you'll get pi minus 2 alpha. So what is sine pi minus 2 alpha? You guys remember the trigonometric circle? We said that sine alpha is the same as sine pi minus alpha. So if I have sine pi minus 2 alpha, it would be the same as sine 2 alpha. So yeah, this is equal to this one. And you guys can see we got the same range for complementary angles. So we can say that two complementary values of the launching angle result in the same value of the range. And it is obvious here. So 30 degrees and the 60 degrees, when you add them together, you'll get a 90. So these two are complementary angles. And you can see that they land at the same spot. So they have the same range. Okay, same thing for the 20 degrees and the 70 degrees. When you add them together, you'll get a 90, and you can see that both of them have the same range. So these are the complementary angles. Now you can click on this fat simulation and let's just apply it to a simulation. Okay, so you guys will get this page. Go to lab. Okay, so choose this one. Okay, so there you go. You have the cannon right here. Okay, you can lift it up, you can keep it on the ground. It's up to you. And this angle right here, you can see it is the launching angle. I'm gonna set it to 45 first because we just found out that 45 at 45 we'll get the maximum range. The initial speed, I'm gonna put it 15. Okay, and you guys can choose your the object that you want to fire. Okay, so I'm gonna choose a car. All right, this is going to be interesting. And yeah, so let's launch it. Okay, so you can see the car. This is the range of the car. Okay, so I can take this one and put it right here and it will give me the range. So this is the maximum range and this is the time it took for it to hit the ground. Yeah, I'm gonna choose another angle now. So I'm gonna choose 30. Okay, and let's try that. I'm gonna choose a cannonball. Let's try it at 30. Okay, so this is where it hits the ground. I'm going to choose a complementary angle to 30, which is 60, and see what happens. All right, so it hits the ground at the same spot. Okay, so they both have the same range. And that is it. We're done with the projectile motion lecture. So we're going to solve plenty of exercises on this in our live sessions. So yeah, just take care and I'll see you soon. Bye-bye.